Hello, my name is Élie Genois and I am a master's student at the Institut Quantique, and I will present you the work we did in Sherbrooke about quantum-tailored machine learning architectures. When we talk about quantum and machine learning, we could define two different axes of research, where on the first we have the physical neurons that perform the computation, and on the second we have the nature of the data or the task that the neural network is to perform. Both could either be classical or quantum. This talk is located in this quadrant, where we use classical machine learning in order to learn from quantum data. The goal of this research is to better characterize and calibrate increasingly complex superconducting quantum devices. The need for improvement comes from the fact that quantum devices are noisy, and obtaining an accurate measure of the state of a quantum device becomes exponentially difficult as the system size increases. Because of that, a heuristic will most likely be required, and machine learning provides an attractive framework for developing such a heuristic. Our approach is then to design a machine learning architectures for inferring the dynamics of a quantum device from time series measurement data that we have access to in the lab. Our vision is to go further than using black box neural networks by leveraging our knowledge of the quantum mechanical properties of the device in order to more efficiently learn from the quantum data. To do so, we must explore the structure of the problem. So let's define a typical superconducting qubit setup. We are using the same setup as this Flurin experimental paper on which we are building on. So first of all, we prepare the qubit in a given state by applying one of the 6 different preparation pulses. Second, the qubit evolves for a given period of time, and we apply a weak measurement probe in blue that gives us some information about the evolution of the state of the qubit. And this information is the time series voltage data, or DM, in blue. Finally, at the end of the evolution, we apply a strong measurement pulse that collapses the state of the qubit on a given axis to yield either a plus or minus 1. To describe what happens to the qubit during such an experiment, quantum mechanics has its own formalism in terms of a stochastic master equation. In details, the state of the qubit is initially described by one of the 6 density matrices. The time series voltage data is then integrated using a stochastic master equation that essentially has a deterministic part and a stochastic part. The final measurement pulse corresponds to a specific projector that yields in a final probability for the outcome. So this entire formalism gives us a complete picture of the state of the qubit, which we call a quantum trajectory. By using this formalism requires us to know precisely the dynamics of the system, which then becomes intractable for multiple noisy qubits connected together in a device. For this reason, we turn to a machine learning formalism that can allow a lot more freedom on the representation used to go from the inputs to the output. So we will use recurrent neural networks composed of a unit cell that is repeated at every new input, as it is a good architecture for modeling time series data. In particular, we use a long short-term memory, or LSTM, unit, a popular architecture that has made its proof on sequential data. So first, the preparation will be encoded to a hidden state using an encoding layer. Second, each point of the time series data will be fed sequentially to the recurrent unit, updating the hidden state. And third, the decode layer will map the hidden state to yield in a probability distribution corresponding to the final measurement. So to train such a model, we use numerical data obtained by integrating the stochastic master equation for different noise realization and for the different preparation and measurement setups. So doing so, we generate 1.5 million trajectories divided into training, validation, and test datasets. So at first, we train a model to predict as well as possible the final measurement outcome, and it yields good results. So here is a representative training for a 64 neurons LSTM, where we see that the neural network rapidly learns to do better than the naive prediction given by the master equation that makes no use of the time series integrated voltage, or the DM. We see that the training and the validation losses both tend to the best achievable value given by the stochastic master equation itself, before seeing some overfitting. If we look at the final state of the qubit, we see that the neural network is able to map the inputs in such a way as to yield in the final probability distribution that is close to the stochastic master equation, or the physical one. And this is quite impressive since the neural network has only access to one sample of the final probability distribution, with the final outcome being plus or minus 1. And those distributions are never the same twice, with different noise realizations. But looking at the quantum trajectory that yield these vectors, we see in blue the actual physical trajectory, and in orange what the neural network learned. So the discrepancy comes from the fact that the neural network is only trained to be good at the end of the trajectory. But we would like to understand what happens before in our effort to characterize quantum devices. So our proposition is then to modify the loss function by incorporating information about the setup and the physics of the problem. To do that, we add different parts to the loss function. First, there is a cross-entropy loss on the prediction for the final measurement outcome as before. This is what was done in this experimental paper. Second, we add a loss on predicting the next voltage of the time series data as a way of exploiting the information about the state of the device that it holds. I will explain in more detail shortly. Third, we add in a similar fashion a preparation loss to make sure that the initial state of the neural network corresponds to the initial state of the qubit. And finally, we exploit an important feature of quantum mechanics, which is the positivity of any quantum state by imposing that the neural network respects this feature. What we have observed is that implementing the loss in such a way significantly helped the model to produce more accurate prediction throughout the entire quantum trajectory, while only giving it information that we have access to in the lab. So let's look at the time series loss component in more details. There is some information about the state of the qubit that is hidden inside the time series voltage data, but it is quite hard to distinguish from the stochastic noise. Indeed, the random increment is of the order of square root of dt, whereas the deterministic part containing the information is scaled by dt, which can be orders of magnitude smaller. So when training on this loss, we see the following, where in blue is what is measured in the lab, and in red is what the neural network predicts it is going to be. Looking more closely, we see that the neural network actually learns the deterministic part of the time series containing the information by averaging out the noise increments, even if the important part is about 20 times smaller. So it shows that the neural network not only learns the training time series, but rather learns how to extract the important information hidden in them, and then it uses this information to yield in more accurate quantum trajectories. Okay, so here we show the performance of the models with the relative entropy, a measure of the divergence between the probability distribution given by the neural network as opposed to the expected one. And we show this at 2 times, at the very end of the evolution and 1/4 through, as it is a more difficult task for the neural network. So as presented earlier, we see that the neural network trained only to match the final outcomes has difficulties matching the probability distribution at earlier times. The time series loss can help for that, as shown in light brown. The quantum Taylor loss in purple shows how it can significantly help to condition the neural network to learn physical trajectories that are closer to the true ones. And finally, in orange-red, we see the best model trained using a combination of all the different losses introduced earlier. We can also change the actual architecture of the recurrent neural network, which is essentially the way the different neurons in the network are connected together. The idea is to simplify the structure of the recurrent unit, that is quite complicated for an LSTM, and to give it the structure of a differential equation, which governs the underlying dynamics that we are trying to learn indirectly with the neural network. We then want to understand the determinant characteristic of the learning. And finally, we want to use this tool on quantum data coming from an actual quantum device in order to characterize it. And we are working with Siddiqui's group at Berkeley on that point. Thanks for watching, and if you have any questions, do not hesitate to contact me.